guys, my name is Daniel Bobini from UCSD. I'm going to chair this session 7A and the next one 7G on hardware security and side channels. Our first speaker is Sandra from the National University of Singapore, who's going to talk about TickTock, detecting microphone, status in laptops, diverging EM leakage of clock signal. Please go ahead.
Yeah, thank you for the introduction. Hey everyone, I'm Soundarya Ramesh, and today I'll be presenting our work TickTock, detecting microphone status in laptops, leveraging EM leakage of clock signals. This is a joint work with my collaborators, Ghazali, Shihun, and my advisors, Manchun and Joe. So laptops have been a constant target for attacks for several years, if not decades. And one of the primary reasons for this is the presence of privacy invading sensors such as microphones on them, which have been utilized by attackers for remote eavesdropping. And this has been backed by several news media articles in the recent past. Apart from remote eavesdropping, there have also been a bunch of microphone related vulnerabilities in popular applications such as Zoom, FaceTime, and so on. And all of these applications have, at some point recorded victim data for longer than they had to. And this brings us to a natural question, like, are there any effective defenses against such intentional or unintentional eavesdropping? So in fact, there are two lines of defenses. One is the presence of hardware kill switches in laptops, which gives users the autonomy to cut off power supply to the microphone when you're not using it. However, this has the disadvantages that it is manufacturer dependent. Most of the popular manufacturers do not support it. And also it requires you to trust the implementation, underlying implementation. On the other hand, there's also software-based defenses where operating systems help you disable or detect microphone activity through software. But all of this is again OS dependent and can be overcome by software compromises. So in light of this, we asked the question, can we design a microphone defense that is robust to software adversaries while also being less dependent on manufacturers and operating systems? So to this end, we propose our approach, TickTock, which actually utilizes the electromagnetic leakage, to detect microphone on or off status. So to give you a quick, usage scenario of TickTock, you can imagine, you are on a phone call talking about something secretive, and you have a laptop open in front of you, which is running a benign looking application, which is in fact recording your microphone and probably sending it over to a remote adversary. So this is where TickTock comes in handy, where TickTock is an external solution that's going to sit in contact with the external of your laptop. And it captures the electromagnetic leakage signals to finally warn the user that their microphone is in use. So before we go into the key idea of TickTock, let's quickly do a primer on digital microphones. Digital microphones convert physical vibrations into digital signals. And this process of digitizing requires an external clock signal, which is provided by another component to the mic. And in turn, the microphone provides its digital data. So it is really this clock signal that becomes key to our idea here. So our key idea is essentially that this microphone clock frequency changes with mic's on or off status. So to give you a quick idea of how this happens, so when the microphone is on, we observe that the clock frequency provided to the mic is typically in the order of lower megahertz, and this is required for the proper functioning of the microphone. So if we look at the corresponding electromagnetic leakage coming out of the laptop, we see that there is a correspondence in energy leaked for that particular frequency. However, when the microphone is switched off, it is provided a very low frequency signal in kilohertz, typically to put the microphone to sleep. And the corresponding leakage here is absent in the lower megahertz range as expected. So it is really this presence or absence of the clock's leakage that serves as the mic's on or off status detection system. So now that we know the key, we understand the key idea of TickTock, let's go into a high level design. So TickTock consists of two phases, the bootstrapping phase, where we try to learn the unknown parameters, and deployment phase where we perform the mic status detection. So in the bootstrapping phase, we try to identify what is the exact microphone clock frequency we're looking for, and also the exact leakage location on the external of the laptop. And both of these are laptop model dependent. So to see how we learn the microphone clock frequency, we essentially put the laptop into two different states, one when the microphone is on, the other when the microphone is off. And we perform EM scans on the external of the laptop to, on a high level, identify the frequency that's uniquely present only when the microphone is switched on. And utilizing this information, we perform a third scan to quantify the leakage at different locations along the scan to finally identify the location of maximum leakage. So once we know both of these unknown parameters, we go on to our deployment where we place the probe at the location identified to check if the frequency of the microphone is indeed present in the leakage signal to finally predict mic status. So for brevity of this presentation, I would just go into one of the challenges we face in detecting the microphone's clock frequency. So one of the challenges is missing energies in the EM leakage due to the microphone clock frequency. And this is something that we observe in more than 60% of the EM traces that we collect. So in order to solve this problem, we propose a robust clock frequency detection module, which is, it makes use of the fundamental fact that the clock frequency contains the fundamental as well as the harmonics. So to quickly recap this, if you look at an ideal clock signal, and if you look at its textbook formulation, you basically see that it is a sum of sinusoids, infinite set of sinusoids, where the highest energy is present in the fundamental, but there are also decreasing amounts of energies present in its multiples, which are typically called the harmonics, right? So the leakage is present in the fundamental as well as in the harmonics. So, our module makes use of this fact to leverage the submultiples of the detected harmonics to finally identify the fundamental. So to reiterate, if we have missing fundamental as well as missing harmonics, we can utilize the detected peaks to identify potential submultiples that have sufficient harmonics and identify such F-mic candidates. However, this process will lead us to many possible fundamental frequencies, and we have a pruning stage, which I wouldn't detail here. So now that we've seen the high-level design of TickTock, I would like to switch gears to talk about our current prototype. So our prototype consists of a near-field probe, which is essentially sitting in contact with the laptop to pick up the EM leakage. And we have a 30 dB RF amplifier and a software-defined radio, which is digitizing the signals, and an RPi, which is running TickTock's core logic. So here I want to show a quick demo of our deployment phase on one of a recent Lenovo laptop. So here we place the EM probe in the identified leakage location. And here we have TickTock's microphone status indicator, which is in real time trying to predict what is the mic status. So to begin with, the microphone is switched off, and hence it depicts green. And now I want to show a quick demo where we're running Audacity, which is an audio recording application, which is starting to record audio. And you can see the moment the recording starts, the indicator changes to red. And now when we stop, it again turns back to green. So this is just a quick demo to indicate the real-time performance of TickTock. So now we'd like to consolidate the results that we've done. So we've tested on a total of 30 different laptop models. And the main result of TickTock is that it works on 27 out of the 30 laptops, which is 90% of all the laptops we've tested. And like you can see, it doesn't work on 3 laptops, and we've identified all of them to be MacBooks. One potential reason could be that there could be attenuation in the EM leakage signal due to its casing. And on the 27 laptops that we successfully identified the clock frequency, TickTock is able to detect microphone status with high true positive and true negative rates, as you can see in the confusion matrix. In fact, if you look at the individual true positive rates, we achieve above 98% across all the laptop models. And for some other results, we've also tested, different recording applications, and TickTock achieves high true positive rates in those and high true negative rates in different non-recording tasks that we perform. And we also achieve, we can detect microphone status in the presence of potential EM disturbances from within the laptop, and work across different operating systems, and also, predict status in real time in less than 0.3 seconds. So here we present some of the potential future direction possibilities for TickTock. So TickTock's approach itself, it does not tie it down to laptops alone because it's more general to any digital microphone. So we do perform tests on other devices such as tablets, smartphones, smart speakers, and so on. And one reason we observe for subpar performance compared to laptops is many of these actually still have analog microphones. While there are many possible evidences telling us that the future is looking more digital, this might be one interesting thing to think about. Can we solve similar problems for analog microphones? And the other thing is, can we detect microphone status from a distance? Because we're all in situations where there are like multiple laptops in the room, maybe this scenario right now, right? So there might be a useful application where you can have one single detector, a tabletop detector that can identify microphone recording activity. And this would definitely require, because there's going to be EM attenuation, there's a need for some leakage amplification techniques. So it might be an interesting future possibility. And there are also a bunch of other interesting things to think about. Can we do mic deterrence rather than just detection, and potentially expand to other potential sensors such as cameras and IMUs, which are also privacy invading today. And that brings me to the conclusion of my talk. So TickTock is an EM leakage-based mic on or off status detection system. The fundamental is basically utilizing the microphone clock frequency itself as a proxy for status detection. And we hope this work can inspire some potential future directions of extending to longer distances and also other sensors. Yeah, thank you.
Thank you for the great talk. Do we have any questions?
Hello. This is pretty interesting. What I'm wondering is, what about for devices that use voice assistants that have a microphone that's on all the time? Do you do any work or have any ideas for classifying potentially adversarial mic on situations versus just mic is on or off?
Okay, yeah, that's a very interesting question. So we did test scenarios, especially in smartphones, which have this always on scenarios. And what we noticed was there is actually an intermediate clock frequency. So there's one clock frequency for performance, high performance, which is the typical recording scenario. And there's also a low performance mode, where it typically takes about 512 kilohertz intermediate clock frequency to for the low power mode of always on detection. So technically TickTock can identify the difference between a typical recording scenario and an always on scenario, like that is looking for hotcodes.
Cool, thank you.
Thanks for the presentation. I'm just really liking a question from chat because
okay.
So the question was, have you encountered difficulty eliminating environmental noise with your SDR?
So yes, environmental noise, especially from devices that interfere in the same frequency range we are looking, is a problem. And in some way, because we're relying on harmonics, which typically makes the clock signal a very wide band signal, typically you wouldn't see noise which is covering the whole range. So we typically see narrow band noise. So there are some other harmonics which we detect, which can always, it kind of leads to high accuracy in detection. Yeah.
What is the frequency range that you actually use?
We're in megahertz. We're looking at the lower megahertz. So typically below 30 megahertz, like 1 to 30 megahertz.
As well, so it's essentially whatever up to 30 megahertz.
Yes. Yeah.
I hope this answered it.
Yeah.
All right. Yeah, one more question. For the presentation. So, speakers affect the detection by those budget shared.
Sorry?
Some budget shared for it is microphone and speakers. So,
Sorry, I didn't get your question.
so I hope that some speakers affect the detection by.
You mean the speaker, loudspeaker?
Yeah.
Yeah, that's actually a great question. So there are cases where the speakers and the microphones do share the clock frequency, which might lead to false positives. But we've seen that the trend seems to be changing, at least in the more recent laptops from about 2018 onwards. We see that of the 6 laptops we tested, only one of them had this scenario of speakers and mics sharing the clock. So it seems to be that, in the future, it might be possible that they don't actually share the clock. Yeah.
All right, let's thanks the speaker.